Hello there, and welcome to Gravitonic. I'm Nick, and today I wanted to do a different video in which I can actually write on a board and make a little bit more complicated arguments instead of just talking and waving my hands around. And as a great start for this sort of video, which I want to know what you guys think about, is why do we need QFT? You see, there are many reasons of why it is difficult to combine quantum mechanics, which I'm going to always write in red, and special relativity, which I'm always going to write in blue. When you try to mix them up, weird things happen, and the resultant relativistic quantum mechanics is actually problematic, and you must go from this thing to something more complicated, which is QFT. And it is really more complicated. To understand why exactly, why you can just pick and write a wave function for a special relativistic particle, I wanted to do this video, which is a very silly calculation and just an example of why things tend to go wrong. Now, the problem is the following. We're going to start with a box. It's actually a one-dimensional box, although I'm drawing it in two dimensions, and it has length L. I'm doing it in one dimension just because it is easier. We're going to put a particle inside it and ask ourselves some properties about this particle. Now, from quantum mechanics, we know that delta x, delta p, the uncertainty of position times the uncertainty of momentum, is greater than or equal to h bar over 2. Furthermore, we know that in order to have this particle inside a box, it makes sense to demand that the uncertainty in position is smaller than or equal to L. Hence, we get that L, delta P, is greater than or equal to h bar over 2. Now, as a silly form of calculation, let me remind you that delta P is actually defined as being the square root of the expectation value of P squared minus the expectation value of P squared, and hence we can get here that P squared is about larger than or equal to delta P squared. Therefore, using this result, we are going to simply write straightforward that Lp is greater than h bar over 2, where this p is understood as being the square root or the expectation value of p squared. Now we have this. I'm now going to wonder about what is the energy of the particle inside this box. We know, we know here that the momentum is larger than or equal to h bar over 2L. Now we know the energy from special relativity is given by m2 E squared equals m2c4 plus p2c2. Hence, it is greater than or equal to p2c2, and therefore quantum mechanics tells us that this is greater than or equal to h bar 2 c2 over 4l squared. Now we have this equation that represents both quantum mechanics and special relativity together. We have that E is always greater than or equal to h bar c over 2L. Now what's interesting about this is the fact that if you make L smaller, so we pick L and make it smaller, this implies that this guy, the energy, gets larger, gets greater. This is why when you go at the LHC and you're looking at really tiny things, the energy, how tiny, implies that the energy is very large. Hence why we need really large energies at the LHC, at the particle colliders, in order to explore what is really tiny. But something that is curious in here is that we can go back to this equation in which E squared equals m2c4 plus p2c2, because you see, at rest, we have that E equals mc squared, which means that the energy of a rest particle, a particle that is not moving, is mc squared. Now, since we can make this energy really big by making the box really small, there is a point at which we can make E greater than or equal to h bar c over 2 L is this, yeah, I copied right, larger than 2mc squared, which means larger than the energy necessary to create two particles. This is going to happen for very small boxes, namely for boxes with L smaller than h bar over 4 mc, which equals 1/4 of the so-called Compton length for the mass m. This means that if you pick a really tiny box, which I'm just going to zoom in here, this really tiny box, you put a particle in here. However, the uncertainty of the energy of this particle is going to allow to create new pairs of particles in here. So instead of having just one particle, you're going to have particle creation and particle annihilation. You can get these two particles annihilating themselves or creating out of nothing due to the energy uncertainty of this single particle you added there. Therefore, when you try to write a wave function for that particle, you won't really be able to manage it because you're going to have a wave function for a particle, but you have to somehow describe the other particles that are being created and annihilated at the very same box. Hence, this wave function approach doesn't work, and instead, you need a new solution. And the solution is, of course, to learn QFT. This is it for today. I hope you liked it, and thank you very much for watching. Cheers.